Hi everyone, this lesson is about optimisation, and we're going to solve this problem, and we've got a little checklist of steps here that we tend to follow. So let's start from the top. Read the question. 1200 square metres of material is available to make a box with a square base and an open top. Find the largest possible volume of the box. Now that's a lot to take in. I'm going to read the question again, but I'm going to combine step 1 and 2. I'm going to draw my diagram bit by bit as I go. So I have 1200 square centimetres of material. That's obviously a key idea, and it's an area, and we're making a box with a square base and an open top. I think I'm going to draw a diagram now. A square base box, so I can draw a square. I'm going to try and draw this in sort of a three-dimensional perspective type of a view, and it's going to have a height. Here we go. So my box is starting to take shape, and that would be the top of the box there, and that would be the edge running down the back. It's an open top. Nice. I'm going to label the base as X by X. That's because it was a square, and I'll label the height of the box H. So far so good. Now we've got 1200 square centimetres available. That's a surface area. What parts of the box? Well, I might draw the box again, but this time as if I've flattened it all out. So I'd have a square. The square would be the base. And now if I did a little cut, if I had my scissors and I cut down each of these edges and the one at the back, but left them joined to the base, I could fold those things out, and they would be rectangles. That would be like that, wouldn't they? That gives me a good idea of the different shapes that make up the surfaces. So I have one square and I have 4 rectangles. Now there's nowhere to read that in the textbook. This is all figuring it out from the clues in the question and using our imagination. So here I go. The area, the total area, would be the square, that's X squared, that's the bit at the bottom, plus 4 times the rectangles, and the rectangles would each be X by H. Now I have a number for the area. The number was 1200. 1200 equals X squared plus 4 times X times H. I can't do much more with that. There's no easy way to simplify that. I notice that I've got 2 pronumerals, X and H. Okay, we'll deal with that in a minute. Now let's go back to the question. I'm just going to tidy that up. That ended up being very messy. I want that to be equation 1. I'll probably have to come back to that. Now what are we looking for? We're looking to find the largest, so it's a maximisation question, volume. Now that's important. The whole question hinges on finding the volume. Now let's see, what have we done? We've done step 2. We've converted the clues into equations. Well, we've started to do that. The clue about 1200 has turned into an equation. There might be more of those coming. And have we identified the variable that is to be optimised? Yes, volume. And have we expressed that as a function of a single variable? Well, no, that's my next part. I need to think about a formula for volume equals. So let's try that. Volume equals, well, for a rectangular shape, it's length by width by height. Now length by width in this case is X squared multiplied by height. The advice said to express as a single variable. So V at the moment is a formula involving 2 variables, X and H. I think I'm going to work with X. So I'll leave X squared, but I need to replace H. I've probably jumped the gun by getting into here. I'm just going to move that off to one side and give myself a little bit more room to play around up here. I'm going to isolate H. I realise there's a gap in my working there. I'll bring that back in a moment. If I want to isolate H, I think I could have 1200 subtract X squared would equal 4 times X times H, and then I could divide both sides by 4x, cancelling those. Now H would be that thing. Okay, that thing is going to go here. It's 1200 minus x squared divided by 4x. And that's, in brackets, it's all multiplied. Wow. I've got my volume as a function of a single variable. So volume is a function of x. I'll just write there, that's a function of x. That's good, that's what I needed. That was step 4. Identify the variable to be optimized, volume, and express as a function of a single variable. In my case, I'm using x as my width of my base. What do we do next? We find the derivative. Okay, that sounds like something we can do. We would probably tidy up a little bit first. I'm going to multiply x squared through this brackets. I would have, oops, didn't mean to stay red then. I would have 1200 x squared minus x to the 4th, all divided by 4x. Now that's the same as 1200 x squared divided by 4x minus x to the 4th divided by 4x. That makes my life better. So that's a 300x. And this bit will be a 1/4 multiplied by an x cubed. That's my formula for volume, and that's a lot better to take a derivative. I wouldn't even know where to begin taking a derivative the way it looked back there. Well, to be honest, I would, but I'm not sharing that at the moment. We're doing introductory level. So dv over dx. Derivative of 300x is 300. Derivative of this one, the cube, the number 3 multiplies by the the constant at the front, and then we reduce the power to 2. That's my derivative. So that tells me how the gradient of the volume function changes. And remember, if I want an optimization, I need to find a turning point. And a turning point is where the tangent would be horizontal. Derivative 0. Here we come. We've got a derivative. We let dv dx equal 0. So 300 minus 3 over 4, and that was a squared, wasn't it? X squared equals 0. So we'll add that to the other side. Now it's probably time to multiply the 4 by the 300, and let's divide by the 3 while we're at it. That's x squared. That becomes 100. So x squared is this? Well, the square root of all of that, I would have 2 times 10, or 20. X is 20, and I think my units are centimetres. Technically, I should say plus or minus 20. I'll do that when making a square root. It could be negative, as in the mathematics tells me it could be plus or minus, but common sense tells me to reject that answer, because I've never seen a box in the real world with a base of length negative 20. It doesn't make sense. Let's go back to our checklist. It's a long way back. Did we find the derivative? Yes. Did we let the derivative equal 0? Yes. Now we have found the value of x that worked for that. We have to test the nature of the turning point. We wanted this to be the largest volume. We have to really hope that that gives me the largest value. So let's do it like this. Let's make a little table of x and dv dx. Now we think 20 is the critical value, and if we were to substitute, there's my derivative. If we were to substitute 20 in at this point, we should get 0, shouldn't we? Let's just do it in our head. 20 squared is 400, divide by 4 is 100, 3 times 100 is 300, 300 take 300, yes, that's definitely 0. So I'll get a 0. Now I want to know what it's like a little bit to the left and a little bit to the right of the turning point. We don't have to go by very much. We could go to x equals 18, and we could go to x equals 22. Now that's going to be a bit more of a difficult calculation. So we'll bring our calculator into the play, won't we? Here we go. Let's go 300 minus 3/4 by 18 squared. It's 57, but most importantly, it's a positive 57. Now let's do this again when x was 22. It's a negative 63. So I've now got that at this point I had a gradient of positive 57, and at this point it was negative 63. I don't really care that the numbers were 57 and 63. I just care about the fact they were positive and negative. If the gradient is positive, it means that the tangent is going upwards. At the turning point, the gradient was 0, so the tangent is horizontal, and at this point the tangent has a negative gradient, it's going down. Boy oh boy, that looks like a maximum to me. So when x equals 20, we do have a maximum volume. Now let's go back to our checklist. We tested the nature of the turning point, verified it's a maximum. Have we actually answered the question yet? Have I calculated the volume of the box? No, I haven't. I need to use, where's my lovely formula for volume? Here it is, here. I need to use this formula to calculate volume, but now I know to put x equal to 20, don't I? So I will have to come all the way down here. So, all right, therefore, V equals, forgot what was written there, 300x minus 1/4 x cubed. 300x minus 1/4 x cubed. Now we determined that the greatest volume happens when x is 20. So that's a 20 cubed over 4. Oh, I'm feeling lazy. Let's get the calculator going. What do I need? 300 by 20. Subtract 20 cubed over 4. We have 4,000. That's our maximum volume. 4,000 cubic centimetres is the maximum volume. Now, I'd like to show how we verify this. So we've done all the working. Let's go to the graphing application, and I'm going to type my formula for volume. 300 times x minus x cubed over 4. I'll draw that. Doesn't look very interesting at the moment, does it? Let's set some sensible values for the view window. It wouldn't make sense for x to be less than 0. Remember, x was the edge of the box. We know that x had to be 20 for this to work, so let's go a bit further. Let's go up to about 50, and we might as well go in steps of 10. I'm not going to change the y values. I still don't see very much, but now that I've set the horizontal scale, I will do a zoom auto, and there's my picture. That's pretty good. So I'm looking for the maximum volume. It seems to be there, doesn't it? I could do a G-solve and then press maximum, and it identifies when x equals 20, the edge of the base, the volume is 4,000, and it even tells me the derivative at that point is a 0. The tangent line would be horizontal. So the graphing app on the calculator really helps me out here. But of course, that's just to verify the solution. The most important part of this is what's here. That's the bit that you'll practice over and over again with every one of these questions you do. Okay, that's been a pretty long video, so if you're still here, thanks for watching.